Hi again. We are going to be looking today at section 2.4, which is the chain rule, okay? So the chain rule deals with composite functions, and it allows us to take derivatives of things that we couldn't do in previous sections. Do you remember what a composite function is? A composite function is obtained by substituting one function into another. Type of notation of this is f composite g. And again, what f composite g of x means is basically f of g of x. It's when you're putting one function inside another function. We're going to call f the outside function and g the inside function. And oftentimes there's like this u substitution thing where this is written as f of u, where the u is really that g of x. So if we looked at something like y equals the cosine of x cubed, the inside function is the x cubed. The outside function is the cosine of whatever. So the outside function is the cosine of u. So f of u is cosine of u. And what are we taking the cosine of? We're not taking the cosine of something just like x. We're taking the cosine of this function, x cubed. And so that would be what the inside function is concerned. And when we have cases like that, we want to use the chain rule. The chain rule says that if y equals f of u is a differentiable function of u, and that u is equal to g of x is a differentiable function of x, then that means that y equals f of g of x is a differentiable function of x. And to obtain dy dx, we can take dy du times du dx. Essentially, when we find the derivative, the dy du, or the f prime of g of x, that's the derivative of the outside. I forgot the word of. The derivative of the outside function. And the g prime of x is the derivative of the inside function. Okay, don't worry, we'll practice that. And those things get multiplied together. Okay, so when applying the chain rule, we want to think about f composite g, or we want to think about f of g of x having two parts, an inner part and an outer part. So this is the chain rule, that the derivative y equals f times u is the derivative of the outer function at the inner function times the derivative of the inner function itself. And again, that can be extended, like if there's a function within a function within a function, and we'll kind of look at that as well. So again, functions can be composed of more than two parts. But as we get used to this, something that might help is just for us to look at functions and for us to identify the outside and the inside functions for each of these composite functions. Okay, remember that our u equals g of x is our inside function, and our y equals f of u is our outside function. Okay, so the outside function is like the big function, the big picture. The inside function is like, what are you taking that function of? So like in this first one, y equals 1 over x plus 1. Maybe it would be easier to start with the outside function. Like what's happening is that in general, this is like y equals 1 over something, right? So we're going to call that something u. And so what is inside that? What is that u? Well, my u is that x plus 1. Let's just do a couple more. I think it'll click in if we do it. In this next one, we have y equals the square root of 3x squared minus x plus 1. So the big picture, what's going on in the big picture? We're taking the square root, right? Y is the square root of something. What is that something? That something is the 3x squared minus x plus 1. Okay. Here, y equals the sine of 2x. In general, we're taking the sine of something. So that's our outside function. Oops, y equals the sine of x. Oh, just kidding, the sine of u. Sorry, got excited. And so what is that u? That u, we are taking the sine of 2x. And then what about the next one? Y equals tangent squared x. Well, some of you might say, well, tangent x, but that's not really what's happening. Look at the big picture. This is really the tangent of x squared, right? We're really taking something and squaring it. So our outside function is really that y equals u squared. And what is it that's being squared? Tangent of x. And again, the more of these you do, you'll get better at being able to tell what your inside and outside functions are, okay? So now that we've had a little practice with inside and outside functions, let's actually find the derivative. Let's find dy dx for y equals x squared plus 1, that quantity cubed. Well, if we want to think about our inside versus our outside function, you guys will have to tell me which one you think is easiest to see. Maybe it depends. For me, I see that I have something cubed. So my outside function, I'm going to think about as u cubed. And what is it that's being cubed? It's that x squared plus 1. So that's my inside function. Okay. So what I want to do is I want to take the derivative. Okay. So if I did that, then the derivative of y would be dy dx. And now I want to take the derivative of the quantity x squared plus 1 cubed. So let me just write that real quick so you see that. So this is what we're taking the derivative of over here. So what that means is that we're going to have to use the chain rule. We want to take the derivative of this outside function. So we want to take the derivative of the whole thing. So let's just do that normally, okay? We can use the power rule. We're going to take 3 times this x squared plus 1 squared, okay? But because there was an inside function, we also need to multiply that by the derivative of the inside function, which is the x squared plus 1. So this is the derivative of the outside function, and we want to multiply that by the derivative of the inside function. Well, we need to find that, okay? So I'll leave this 3 times the quantity x squared plus 1 quantity squared, and now I want to multiply that by the derivative of the inside function. The inside function was x squared plus 1. The derivative of x squared plus 1 is just 2x. And so what that means is that I can write my derivative, dy dx, can multiply this together and get 6x times the quantity x squared plus 1 squared. Okay, you could multiply it out if you wanted, okay? So another thing that you could do, or if you wanted, you could multiply this out. It ends up being 6x to the 5th plus 12x cubed plus 6x. So you could multiply that out if you wanted, okay? But it's fine like this as well. And this problem is something that you could initially revise. Like you could have written this out as x to the 6th plus 3x to the 4th plus 3x squared plus 1, and then found the derivative, okay? But that's not really a practical approach if we have something like to the 20th power. So if it was cubed, yeah, we could revise it using the pattern there, but this is probably a better rule for us. And so this brings us to this general power rule. It's a special case of the chain rule, and it's when we have an inside function where basically we're the outside, okay, we have an inside function that's part of that power, okay? So it is used for problems in the form y equals u of x to the nth power. So it's when you have some sort of function raised to a power, just like we did here. We had this x squared plus 1 raised to a certain power. And that general power rule, we're just going to apply exactly what we did. We can take the exponent, turn it into the scalar multiplier, take the derivative of that outside function. So basically take the inside function to the n minus 1, and then take the derivative of the inside function, okay? I think it'll be best if we just get some practice, okay? And we'll get that a lot in example 3. Okay, I've got 5 questions here in example 3. So we want to find the first derivative. So letter A has f of x equals 3x minus 2x squared cubed. Well, I can see that this is one of those special cases, right? I see that I have something cubed, and that's my outside function. And then the inside function, what is it that's being cubed? 3x minus 2x squared is the inside function. Oops. And that's going to equal, u. Okay. That's my inside. All right. So let's take the derivative of that. So I can call this f prime of x if I wanted, or df dx, whatever you want. Primes never show up. And I want to take the derivative of the whole thing. So that means I can take 3 times 3x minus 2x squared squared. So I'm just using the power rule. But because there was an inside function that was something other than just plain x, now I want to take the derivative of the inside as well. Okay. We didn't have to do that before, because before our inside function was just x. And what's the derivative of x? 1. So it didn't matter, right? But if you have something other than x, we need to include that derivative, okay? So I'll just rewrite this again. 3 times 3x minus 2x squared squared. And now I want the derivative of this. So that ends up being 3 minus 4x. And I guess that's fine. So that's good. We can't really, I mean, you could distribute if you wanted to, but there's nothing really that we could deal with there. I mean, it might be written, I mean, just so you know, like sometimes, and I don't like it either, but sometimes they'll like multiply these together in the answer, and they'll have like 9 minus 12x times 3x minus 2x squared squared as the final answer, or something like that. It bugs me. I mean, that has a common factor, and so does this. But again, it is the derivative, so you're good. Okay. Let's look at letter B. We have g of t equals -7 over 2t minus 3 squared. That quantity squared. Now, what I might do is revise this a little bit. I would probably, because we, just like we did in the other quotient rule problems, wouldn't it be nice if we brought this up and thought about this, not quotient rule, sorry, power rule questions, where when we have a quotient that's down here, we can just bring it up and apply the power rule instead of the quotient rule. Let's maybe try that instead. And what we could do here is, when we're taking g prime of t, we can pull out that -7 and then really take the derivative of 2t minus 3 to the -2. Now, again, if we're thinking about outside functions and inside functions here, our outside function would be u to the -2, and the inside function would be that 2t minus 3 equals u. Okay, so let's just think about that when we're finding the derivative. So I'm going to keep this -7 out here. And now I want to take the derivative of this whole thing. So that would be negative 2 times 2t minus 3 to the negative 3. Okay. But now I need to take the derivative of the inside function, d dt of 2t minus 3. So again, I've got negative 7 times negative 2 times the quantity 2t minus 3 to the negative third. But now I want to multiply by what the derivative is. So the derivative of 2t minus 3 would just be 2. And then I could, just simplify that a little bit. I'm multiplying all these things together. So negative 7 times negative 2 is negative 14 times 2 is 28. So I've got 28 times 2t minus 3, that quantity cubed. So essentially that means that my g prime of t would be 28 over 2t minus 3 cubed. Because again, the rule is to try to get no negative exponents in the final answer. So even though it helped us to think about it with a negative exponent, we'll eliminate it from our final answer. Okay? Okay. Again, the secret is take the derivative of everything, but if the inside was more complicated than just t, or just x, or just theta, you've got to take the derivative of that as well. Okay? Letter C. We have f of x equals x squared times the square root of 1 minus x squared. Well, I've got some news for us. Do you guys see what we've got here? We have the product rule. That's right, folks. We get to utilize a lot of things here. So look here, if we're looking at the product rule, the two things we have is we have that x squared, and then we've got the square root of 1 minus x squared. So if I'm taking f prime of x, remember that the product rule means I'm going to take x squared times the derivative of 1 minus x squared to the 1/2. So I'm just rewriting the square root as that to the 1/2, okay? And then plus 1 minus x squared to the 1/2 times the derivative of x squared. Okay, so remember the product rule that we had? So we'll still be able to apply that. So I'm going to leave the x squared as is. But now what I want to do is I want the derivative of 1 minus x squared to the 1/2. Well, we have something to the 1/2 power, but that something is not just plain x. That something is 1 minus x squared. So I'm going to have to apply the chain rule on when I take the derivative of 1 minus x squared quantity to the 1/2. So if I use this power rule, that means I'm going to end up with 1/2 times 1 minus x squared to the negative 1/2. But then I need the derivative of the inside function, which was 1 minus x squared. Okay. Now I have plus, and then I have this 1 minus x squared to the 1/2. And now I want to take the derivative of x squared. Well, we have something squared, and that something is just x, no chain rule. So we can just turn the derivative of x squared into 2x. So that's good. Okay. So I've got this x squared, and then again, using the chain rule, I still have this 1/2 times 1 minus x squared to the negative 1/2. But now I'm taking the derivative of 1 minus x squared. So using our knowledge of derivatives, that's going to be negative 2x. And then I guess I could start cleaning this up a little bit, huh? So I would probably rewrite that as 2x times the square root of 1 minus x squared. Okay. And then I can start cleaning the rest of this up a little bit too. So if I multiply these together, these 2's cancel, and I've got x squared times x and negative. So I have negative x cubed and then over 1 minus x squared, the square root. So basically 1 minus x squared to the negative 1/2 means that the square root of 1 minus x squared would be in the denominator. And then I have this plus 2x times the square root of 1 minus x squared. So let's maybe create a common denominator so that we can combine the terms together. I can multiply by root 1 minus x squared over root 1 minus x squared. And if I did that, that would give me negative x squared. So in the denominator, I would just have the square root of 1 minus x squared. And then here I would have plus 2x. Oh, and look, when I multiply these together, we end up with 1 minus x squared. So let's distribute. That gives me negative x cubed plus 2x minus 2x cubed all over the square root of 1 minus x squared. And so that looks like about it. I can combine then negative 3x cubed plus 2x over the square root of 1 minus x squared. Okay. We usually don't rationalize the denominator. Okay. Like, you know, sometimes rationalizing the numerator is a strategy, right? So when we have the derivatives, and I know it seems counterintuitive to everything we've done, you don't have to rationalize the denominator. You can leave it like that. If you do rationalize the denominator, it's not wrong, but you can save yourself a step just by leaving it like that, okay? All right, letter D, y equals x over the cube root of x squared plus 4. Now in letter B, we had a quotient, but we could just bring the other one up. Here, regardless, we've got basically like one type of function in the numerator and another in the denominator. So this means we're going to have to use the quotient rule. Okay. So our x is going to be our numerator, our high, and our cube root of x squared plus 4 is going to be our low. All right. So y prime is going to be low. And again, usually when I'm doing the manipulation, it works. It's usually a little easier if you have a radical to turn it into a rational exponent so that it's easier to apply the power rule, okay? So, so I'm going to take x squared plus 4, that quantity of the 1/3, and then I want the derivative of the numerator. So low d high minus high d low. Oh, let me rewrite that. Let me write that as x squared plus 4 to the 1/3. Be easier for us to see, okay? So again, I have so low d high minus high d low all over low squared. Okay. So let's try to do a little bit with this. So I have x squared plus 4 to the 1/3, and now I want the derivative of x. That's nice. That's just 1. Okay. Minus x, and now I want the derivative of this. Uh-oh, we've got a function raised to the 1/3 power. So we're going to have to use the chain rule. So we're going to want the derivative of this whole function. So that's going to be 1/3 x squared plus 4 to the negative 2/3. And then we want to multiply that by the derivative of x squared plus 4. Okay. Oh, and then still over, and then I'll just write this as x squared plus 4 to the 2/3. Okay. So then that would be just x squared plus 4 to the 1/3. And then I still have minus x. And now I'm going to have the 1/3 x squared plus 4 to the negative 2/3. But now I want the derivative of x squared plus 4. That's just going to be 2x. And then again, still all over x squared plus 4 to the 2/3. Okay. We could combine those together if we wanted. Like on the left there, if we wanted, we could multiply by 3/3 to get rid of this 1/3 that's here. Can I do that? Is that good? And again, your steps might vary. You might do it differently. Here I end up with 3 times x squared plus 4 to the 1/3 minus, this ends up being 2x squared, those 3's will cancel, times x squared plus 4 to the negative 2/3 all over 3 times x squared plus 4 to the 2/3. Okay. And now at this point, this kind of looks like a hot mess, right? But way at the beginning of the year, what we did is we practiced. You see that there's that we can factor something out. And again, we want to factor out, if you think about it like the lower of the exponents, like if you had 4x cubed and 3x squared, you'd factor out the x squared because it was the lower of the two exponents. That's what we're going to do up here in the numerator. We're going to want to factor out the common factor. So the common factor we can factor out is x squared plus 4 to the negative 2/3. And let's see what's left. If I factor that out here, I have 3. And then I subtract exponents. 1/3 minus negative 2/3 is 3/3. Oh my gosh, that's just x squared plus 4. And then if I factor it out of here, I just have minus 2x. Oh, and that's it here. And then I have 3 times x squared plus 4 to the 2/3. Well, let's bring this negative exponent down. So that means that I would have 3 times x squared plus 4 to the 4/3, because when I bring it down, we have the same base, we add the exponents. And then do you want to distribute in the numerator to save a little bit of time? I can see that if I do that, I can combine my like terms. So I have 3x squared plus 12 minus 2x squared. So I can combine 3x squared and minus 2x squared to get x squared plus 12. And then in the denominator, I have 3 times the quantity x plus 4, to the 4/3. And that is my y prime, or my dy dx. You couldn't do that 3 days ago, huh? It's exciting. Okay. So again, that's using the chain rule along with the quotient rule to help us find that. It's really important that, again, if you ever are doing something to a function other than just x, you've got to use the chain rule. All right, let's try one more. Y equals 3x minus 1 over x squared plus 3, that quantity squared. Well, there are a couple ways you could think about this. All right, what I'm going to do is I'm going to think about using the power rule and the quotient rule. So this whole thing is my outside function, and then this part is going to be the inside function. All right, So to find my derivative, my y prime, that means I'm going to take the derivative of the big function. So that's going to be 2 times 3x minus 1 over x squared plus 3 to the first power. But now I want the derivative of 3x minus 1 over x squared plus 3. Okay. Oops. So when I take the derivative of the 3x minus 1 over x squared plus 3, do you see what we're going to have to utilize? Notice that here we're going to have to utilize the quotient rule. Okay. So when we utilize the quotient rule, what that means is that we're going to have low d high, so the derivative of 3x minus 1, so that's 3, minus high d low, it's going to be 2x, over low squared. Okay, hopefully we're at the point where we can do that without writing out all the derivatives. That one was a little crazy, so I wanted to remind you of that. So let's clean this up a little bit. This can still be considered, I mean, I guess you could write this as 2 times 3x minus 1 over x cubed plus 3. Remember, 2 is not 2 over 2, it's 2 over 1. And I guess we could maybe distribute here a little bit. So that would give me 3x squared plus 9. Negative 2x times 3x is negative 6x squared. 1 times 2x is 2x, all over x squared plus 3 squared. And if I combine like terms here, I end up with negative 3x squared plus 2x plus 9 over x squared plus 3 squared. And essentially now I just have a bunch of factors. So I could think about like this as a factor, this down here as a factor, and I could just combine those together. So my y prime could be, my factors in the numerator are 2, 3x minus 1, and negative 3x squared plus 2x plus 9. And then my factors in the denominator are x squared plus 3 and x squared plus 3 quantity squared. So what happens when we put those together? X squared plus 3 quantity cubed. Let me make sure I did everything right. Good, that matches. Okay. And there you go. All right. So that is a little bit about the chain rule. So again, the biggest issue is that students will tell me that this is the answer and not take the derivative of the inside function. And the derivative of the inside function, as you can tell, sometimes creates some really important parts of that derivative, right? So happy chain ruling, chain, chain, chain.